All right. It is such a pleasure to be here at the World Science Festival. This week is, for scientists, is just so much fun. So we're going to start today with a question, which is, how do you observe something you can't see? And this is a key question if you want to find and study black holes, because black holes are objects whose pull of gravity is so intense that nothing can escape them, not even light. So we can't see them directly. The story I would like to share with you this morning or this afternoon is how we've been able to find a supermassive black hole at the center of our galaxy. And this has provided us with the best evidence to date that these exotic objects truly do exist, which gives us a wonderful laboratory for understanding the physics of these objects, how they warp space-time, and the astrophysics of these objects, what role they play in the formation and evolution of galaxies. So to begin with, we all have to agree on what a black hole is. So it seemed very appropriate to put up a blank slide. So while black holes require relatively exotic and complex physics to describe, the way I would like you to think about a black hole is the way I actually think about a black hole on an everyday basis. So a black hole is an object with mass, but this mass is confined to an infinitesimally small volume. So if we think about density, which is mass divided by volume, the density goes to infinity. And in physics, anytime we have the number infinity, that's known as a singularity, which is like a big red arrow that says you do not have your description of the physical world right here. And of course, in physics, that means that we don't actually know how to make the world of general relativity, which is the study of gravity in its most extreme form, and black holes definitely have a lot of gravity, work with the study of quantum mechanics, which is a study of things that are very small. Of course, black holes are infinitesimally small, so they qualify. So when we figure out how to make these two aspects of physics work together, we will understand what a black hole actually is. But today, we don't. But fortunately for me, there is a size that we can associate with the black hole. So it's a virtual size. It's not a surface of the black hole, because the black hole has no finite size. And this is known as the Schwarzschild radius. It's popularized by Star Trek as the event horizon. It's the point of no return. So light, the last point that light can escape from the gravitational field of the black hole, is this event horizon, or Schwarzschild radius. It's also important because every object of a given mass has a Schwarzschild radius associated with it, and it simply depends on the mass. And why is this radius important? It's important because if you can figure out how to squeeze that mass down to its Schwarzschild radius, gravity will overcome all other known forces, and the object will collapse to the infinitesimally small object. So if you want to prove that there is a black hole out there in the universe, that these objects really do exist, your job is to show that there is a mass inside a very small volume, and the volume that's set by this Schwarzschild radius. And it depends only on mass. So the more massive the object is, the larger the scale is, or the size is. So if we were to take the Earth and squeeze it down to the size of a sugar cube, it would be forced to become a black hole. If we were to scale up and consider the sun and squeeze it on down, and of course I had to put UCLA in there because that's where I'm from, but take any college campus pretty much, and the sun would become a black hole. Okay, so now we have what is a black hole and how do you prove that these things exist? So now let's talk about where black holes appear. And the black holes that I'm fascinated by are the supermassive black holes, and I'll get back to what that means. But in astrophysics, there are two classes of black holes. The ordinary black holes, as if there could be such a thing as an ordinary black hole. And these were thought of from theoretical studies first. So theorists who were contemplating how stars, the most massive stars in our galaxy, would go through, would evolve throughout their lives, understood that at the end of their life, the inner parts of the star would collapse to form a black hole. The outer parts would explode and expand in an explosive way and form a supernova. So that's what we're actually seeing here. This is a supernova remnant. So it's the outer layers of a very massive star, a star that started its life off with roughly 30 times the mass of the sun, ending its life in this explosive way. And the thinking was it would form a black hole of roughly 10 times the mass of the sun. So thought of from a theoretical perspective, and then observations have come along to prove that these objects truly do exist. And that's been known for a long time. And LIGO, the gravitational wave detector, put the evidence for the stellar mass black hole in a whole other regime. So that is the final point on the stellar mass black holes. Now, the story about supermassive black holes is very different. The story of supermassive black holes come from the study of galaxies. So galaxies, there are a lot of galaxies, actually, if we look at the next one. This is a picture from Hubble Space Telescope. And everything in this picture is a galaxy, except one object in the middle, which is a star in our own galaxy. And the scale here is, you can understand, is different because each galaxy has roughly 100 billion stars. In the last picture, we were looking at a single star within our own galaxy. And what we're looking at is pictured optical wavelengths, which is what your eye detects. And you see the light from the stars that are like our sun. And there's nothing unusual about this picture to lead us to conclude that there are supermassive black holes. But roughly 10% of all galaxies, if you look at them in radio wavelengths, long wavelengths, where your cell phone works, roughly, you see something truly spectacular. At the center of the galaxy, the starlight is now no longer visible, and you see a mission coming out, these jets, and the jets are moving tremendously fast. So you know that there's something powerful at the center, at the heart of these galaxies. And at the heart, we also see a dot in the middle, and that dot has emission or light characteristics that look nothing like starlight. And it was thought, or speculated when these objects were discovered, that what we're seeing here is the dining habits of really massive black holes. So matter is falling onto this black hole and powering these jets. So you can think of these as black holes, which are roughly 1 million to 1 billion times the mass of the sun, so much more massive than the stellar mass black holes, that are having a Thanksgiving feast. You know, they're definitely indulging, and we see the light of the feast, because remember, you can't see light inside the event horizon. Okay, now those are, could call them maybe the prima donnas of the extragalactic world. They're kind of show-offs. They're only a small fraction. But it did lead to the question, roughly 40 years ago, do all galaxies harbor supermassive black holes at their centers? And if we are going to entertain that notion, then our galaxy is certainly the best place to look, because it's the closest center of a galaxy that we'll ever have to study. So this is a picture of one of those galaxies that would presumably look pretty much like what our own galaxy would look like if we could get outside it and look back at it. Galaxies, for the most part, are flattened disk-like structures. In our own galaxy, we have these beautiful spiral arms. But of course, we're not looking at it from the outside. We're looking from it from the inside. And from an inside vantage, our solar system is about halfway out in the galaxy. So if we look in the night sky, what we're seeing in terms of this flattened disk-like structure is we're seeing the plane of the galaxy. So this is a picture of the Milky Way seen from Hawaii. And you see the light, and in fact, this is why it was called the Milky Way. The Greeks, the word galaxy comes from gala, which is Milky Way. So we see a path that looks kind of milky from all the starlight. But we also might notice that in this Milky Band, that there's a lack of light. And that lack of light comes from dust in the plane of our galaxy. I'm from Los Angeles. I have a very good feeling for what dust in the air does to you. It's like smog. So our galaxy's kind of smoggy. And what you know from visiting a smoggy city is that if you look with your eye can't see very far through the smog. So in Los Angeles, you don't see the local mountains very clearly on a smoggy day. So in the center of our galaxy, there's light coming out, and only roughly 1 out of every 10 billion light packets or photons makes it to us. So that's why the center of the galaxy is not observable at wavelengths that your eye detects. Now, if we go to the infrared, which is just longward of where your eye detects light, or where your TV remote control works, you get 1 out of every 10 photons coming to you. So you can actually see the center of the galaxy. So a key aspect of the work that I'm sharing with you today is the advancements that have been made in infrared technology, your ability to see this kind of light. Now, if I want to show that there's a black hole at the center of the galaxy, the key way to do this, or a direct way to do this, is to look for the stars that are as close to the center of the galaxy as possible, and to watch or measure how these stars orbit around the center. This is tracing or seeing the black hole through the gravitational influence on the stars in the very same way that we could actually measure the mass of the sun by measuring how the planets go around the sun. So what I need to measure is how long it takes that star to go around, and I need to measure the size of the orbit. That gives me the mass, so that's number one. Once I know the mass, I know the Schwarzschild radius, and each orbit gives me a size as well. So I have a mass and a size by approaching the problem this way. Now, what does this mean? This means that I'm inward bound. What I want is to see the stars that are as close to the center as possible so that I can confine the mass to as smaller region as possible. Okay, this tells you why I wanted more than anything else to have the job that I have today. I have my dream job. I feel incredibly fortunate. The University of California and Caltech co-own the largest telescope in the world. So why is this important? It's important because large telescopes come with 2 campaign promises. One is that you build a big telescope, and we describe how big a telescope is by the size of the mirror, the collecting mirror. And if you have a big collecting mirror, you can see things that are very faint. It's, because it's like a light bucket. You're collecting the photons that are raining in. So the bigger your light bucket, the more photons you can collect in a certain amount of time, which means that you can see things that are very faint. And in astronomy, faint means distance. So most astronomers really care historically about this aspect of being able to see the most distant universe, to be able to see the earliest moments in the universe, because light takes a finite amount of time to get from distant objects to us. It's like getting a history lesson. So it's a really important aspect of large telescope. What I care about is actually the second campaign promise, which is the larger your telescope, the bigger your diameter of the mirror, the smaller the detail that you can see. And the way I like to describe this aspect, your ability to get high angular resolution, is to make the analogy to the painting style of pointillism. So pointillism is made with a bunch of dots, and the closer you get to that painting, the better your ability to see or resolve the dots. If you stand further away, it all blurs together and it makes for a beautiful painting. So I want to see the dots. I want to see the dots that are as close to the center of the galaxy as possible. So I want to get my hands on as big a telescope as possible and to develop techniques that really take advantage of this aspect of telescopes. So this is why I love working at UCLA to work with this fabulous facility. Now you might ask, where is this facility? This is like asking, where is my lab? Well, you might say Los Angeles, but I'm going to tell you, actually, it's Hawaii. My lab is in Hawaii. Hawaii on the Big Island. So actually, the Big Island has been in the news quite a bit recently because of the volcano. So it's useful to remember Hawaii is a volcano. And I'll explain why the astronomers still think that Hawaii is the best place in the world to build big telescopes. So we're on the top of Mauna Kea on the Big Island. And the reason why Mauna Kea is such a fabulous place to build telescopes is that it's, for one reason, it's a very high peak. So we're up at 14,000 feet. So if you want to build a telescope, you want to get it on as high a peak as possible because you want to see through the atmosphere. And this is a picture that I actually took on the first time, my first trip up to the top back in 1994. And you can see the clouds below you. So that's useful because if you're like me and think of Hawaii, I usually think of a tropical place with lots of rain. That's not good for astronomers. And the reason why this makes sense is all of that is below you. Now, it's also true that 14,000 feet is a very challenging place to work in terms of human physiology. It turns out your brain doesn't function particularly well up at 14,000 feet, which is an interesting challenge. So you have astronomers, astrophysicists who desperately want to use this facility. The typical UC astronomer might get 2 nights a year. The operational cost of this telescope is evaluated at roughly $100,000 a night. So you do not want to be at suboptimal during your night of observing. And there are classic stories, like the astronomers who will write down the list of everything they should remember and then forget the list. Or in my case, the first time I went up with a graduate student, my first graduate student, we had an interesting debate up at the top, which was, what's 128 divided by 2? So these are one of the aspects that make doing astronomy challenging. So the way we do astronomy today has evolved quite a bit. We now no longer go to the summit. For many years in this experiment, we did go to the summit, which was an exciting adventure, and I loved going up there. But then it became possible to observe from the headquarters, which are in Waimea. There's about 100 people, 100 staff that are responsible for the operations of this facility down there, and it turns out you think much better at 1,000 feet. So that's wonderful. And now, since roughly the last 10 years, it's possible to control these facilities from campus. So now we work in concert with those people who are operating the telescope, but as the scientists, we can do this from campus. So every place comes with pros and cons. This is always the way it is with advancing technology. You get something, and you also lose something. So the things that we gain are better thinking, and certainly better educational opportunities by bringing the observations back to the campus. All right, now let's come to the volcano aspect of this. So the Big Island is composed of 5 volcanoes. One of them is active. That's Kilauea. That's the one in the news. And fortunately, it's a volcano. All the volcanic activity in Hawaii is for the most part pretty calm and not extremely explosive in the sense that you have seen in the news plumes, but you haven't seen anything that throws the dust up into the higher levels of the atmosphere, which would really be a problem for astronomers. But Mauna Kea Kilauea is a different kind of volcano. This is a picture of Kilauea from 1994 when it was in a similar state where you could actually see surface flows. So it is an interesting and exciting place, but we can carry out our observations during this. In fact, we had a night the other night where we could actually see an eruption that appeared on the front page of the Los Angeles Times the next morning. So it's exciting, but it does not disrupt. Mauna Kea is a dormant volcano, which means, according to the geologists, it's not going to do anything for another 1,000,000 years. Now, I have to trust them because I'm married to one, so we hope they got that right. Now, the other reason why the Big Island is such a great place, and in particular Mauna Kea, to build telescopes is that you want not only a high site, that gets you through most of the atmosphere. But the atmosphere that you have left, you want the airflow to be very smooth, what the scientists call laminar. And to get very smooth airflows, you want to be around a large body of water. So to be on an island actually optimizes this. So if you look at the forefront facilities that are built today around the world, you'll notice they're on high peaks near big bodies of water. So the Andes in Chile, the Canary Islands, and the Hawaiian Islands. And that's the reason you're getting this very smooth airflow for going to a high peak near a big body of water. Now, the next thing you want for a large telescope is a dark site. You work very hard to collect these precious photons from across the universe or across our galaxy. And they've been traveling to us for a very long time. In the case of the galactic center, the center of our own galaxy, those light packets, those photons, have been traveling to us for 26,000 years. So the last thing you want to do is have them messed up in any way or contaminated. So a dark site where you don't have local light is incredibly important. So this introduces a very interesting tension in the world of astrophysics, because you want to be both in a very dark place and you're trying to build incredibly advanced technological buildings and facilities and instruments. So you want access to high-tech industry. That tends not to be in dark places. So you're trying to optimize this trade. So Hawaii is one of the few places in the world that provides you with relatively good access to high tech, both in terms of the industry and the people. It gets satisfied nicely in Hawaii. So you want it high tech and you want it dark. So that's the piece about the darkness. Okay, so now we have a telescope, we have it in Hawaii, we've explained why we want it in Hawaii. Let's come back to the problem or the promise of getting very high resolution information, the second campaign promise. So the problem is, while it's high, you're still looking through quite a bit of atmosphere. And it's smooth, but still not that smooth. And you can see that by looking at this picture. These are data that we took when this experiment started back in 1995. It was the original data type. And the trick there was just to take lots of short exposures, and you freeze the interfering effects of the Earth's atmosphere. And if there were no atmosphere, each of the 5 stars that we're looking at here prominently would be the size of the smallest structures that you're seeing and rock solid. That's not what you're seeing. You're not seeing this because these photons that have been coming to us for 26,000 years hits the top of the atmosphere 30 microseconds before it hits your telescope. So they say accidents happen close to home, and that's true in the case of these photons. Okay, so I'm super interested in how do you overcome this problem? How do you beat the atmosphere? Oh, and I should also say another analogy for how to think about the problem with the Earth's atmosphere is think of a river moving by you, and you're trying to look at a pebble on the at the bottom of the river. And if it's moving and turbulent, it's very difficult to get a picture of the pebble. That's what's happening here. I'm trying to see through a stream of atmosphere that's turbulent. So the analogy works fairly well. The other analogy that I like to make in terms of what's happening and what we're trying to accomplish is to think of a circus funhouse mirror, and it distorts you. So that's what's happening to the starlight. It's getting distorted. And I want to figure out a way of putting a second mirror in there, or some process that makes me look flat again. Okay, so astronomers have looked and thought about this for a long time. So if you want to beat the atmosphere, one very straightforward and effective way of doing this is you get above the atmosphere. And that is the solution of the Hubble Space Telescope. It is an incredibly powerful telescope that is not affected by the Earth's atmosphere. So we use this for our work, but the reason why for the work that I'm going to just share with you today, that I'm sharing with you today, that Keck is the choice instrument, is because it's bigger. So the diameter of the Hubble Space Telescope is 2.4 meters. The diameter of Keck is 10 meters. You want to kind of visualize that. That's like the width of a tennis court. And the power of the diameter for the kind of work that I do goes as the diameter to the 4th power. So I've got a telescope that's 4 times bigger. So that's 4 times 4 times 4 times 4. And because I'm not at the summit of Mauna Kea, I actually can do that math. And that's a factor of 100 better in principle, if I can figure out how to make that, to take the blurring effects out. So as you might imagine, if you're being offered the opportunity to do something 100 times better, you're probably going to work pretty hard at it. So that's what I've spent a large part of my career thinking about, which is what techniques can we use and develop to beat the atmosphere. One of my advisors said when I was a grad student, you know, Andrea, you just take the twinkle out of stars. That's my job. So this is an animation that shows some of the work that we've done. It captures what happens if you take a very long exposure in time on the center of the galaxy. So you can see the 5 bright stars that we were seeing the bug splat patterns for a moment ago. And those were short exposures. Those were 1/10 of a second. And they're at 2 microns. That's the wavelength that we do our primary work at. And if we use these techniques, we can get to the highest resolution afforded by the telescope, which is the resolution is about a factor of 20 times better. Okay. Now, the technology that we've been using and developing has changed radically over the last 20 years. So this project is very much technology-driven discovery. So at each phase, where we are in our technological development has sort of dictated how much science we can do. And I have to share, this has been an incredibly exciting journey. When I first started this project 25-ish years ago, I wrote my first proposal. I was a brand new assistant professor. I thought I had such a good idea for how to use this telescope in a new and different way. And you have to apply for telescope time. And this committee, this group of people said, well, this idea that you have for how to collect the data probably won't work. And even if you do, you probably won't see stars at the center of the galaxy. And even if you do, that are close enough, and even if you do, you won't see them move. Okay, so that's a lot of no's to get at the beginning. But fortunately, I'm used to being told you can't do something as a woman in physics. So I said, okay, fine. I've heard that before. Let's keep going. And I also work in a department that is, I'd say, very supportive. So these are colleagues, and I think this is a comment on how science works. You can't do it in isolation. You actually need the support of others to be successful. I think there was a comment in the gala about that just so resonated with me. So I had a colleague who lent me his telescope time, which is, you can't give it back, you know? So enabled us to show that this technique would work. And this is just a picture showing the original instrument. So it was an instrument that was designed for the facility, and we just built, this is in collaboration with my colleagues, a little adaptation that allowed the instrument to see on a smaller scale than it was designed to do. And I think this is also an interesting comment. This is a $100, $200 million scale facility that they're letting an assistant professor come and add a little tweak to it. That is also a rather amazing comment about this particular facility in terms of its willingness to engage in doing something different or outside the box. Okay, so this was what we did for the first 20 years. It was hardware simple, which means not very expensive, computationally complex. So you basically take a little bit of data back and you spend a lot of time developing software and algorithms to figure out what did the atmosphere do versus what's the true underlying object. And there are a lot of people out there who care about that. It's not just the astronomers who think a lot about seeing through the atmosphere, both up and down, and working out the image. That's the military, if you hadn't figured that one out. there is also the whole medical industry that's interested in imaging through tissues, either through your eye or various parts of your body, and want to figure out what you're trying to see underlying some distorting media. So from a technique perspective, there's a lot of reasons to think about this outside of astronomy. It's not why we do it, but we want to see the universe. Okay. The way this story evolves now is that there's a hardware solution to this, and this is a solution that was developed by the military. And as the astrophysics community was making progress in figuring out much more sophisticated hardware solutions, the military basically said, oh, and I should say, the funding for astronomy and astrophysics is nothing compared to the funding in the military. So as we were starting to ask for funding to do this, the military said, basically, we know how to do this, and declassified it. So in the mid to late 90s, there was this huge thrust forward because of a declassification. And this was really exciting, and I was really excited because I knew this would be a completely revolutionize what we were doing at the center of the galaxy. Now, this animation shows both a couple of miracles, like the dome going away, but it also is designed to help us talk about how does adaptive optics, which is this new technology, work. So we see a beam of light coming into the telescope. The mirror was the thing it bounced off of, and then it goes into an instrument bay. And the instrument bay is where all the magic happens for correcting or taking the blurring effects out. So we're going to see both the beam of light, and in a minute, it's also going to be shown in a second way you can talk about light, which is a wavefront. And if there were no atmosphere, each wavefront would be a flattened pancake. So you can see in this the beam going through, bouncing off various mirrors. And if you don't do anything, it's that bug splat pattern again. And it's going to show you a very important element. This is called the deformable mirror. This is the second Circus Funhouse mirror that takes out the distorting effects. So rather than pancakes coming in, we have Pringles potato chips. And then you have the second mirror that when it's not on, doesn't do anything. But if it starts to look at what the past wavefronts look like, then it bounces off into these flat pancakes. So if the system works, fully understands or can fully probe the atmosphere, it is a perfect image at the end of the day. So it gets nice and tight. And for the first time in our work at the center of the galaxy, we can take an exposure that's longer than 1/10 of a second. So the kind of work that we can do is so much more powerful with this technology. Okay, and now you might ask, how do you know how to move that deformable mirror? And a key aspect of that is that we shine lasers into the atmosphere. And we do this because up at about 90 kilometers, there's a very thin layer of sodium atoms, just a fluke of nature. So I love shooting stars, or making a wish on shooting stars, because those are not really stars. Those are meteorites or meteors coming through the atmosphere and burning up. And the sodium atoms in those meteorites or meteors get trapped at 90 kilometers in this very thin layer that's about 4 kilometers thick. So you can take a laser that's tuned to a transition in the sodium atom and stimulate those atoms to shine. So that's an artificial star. And we can then look at that artificial star. We can create it in any direction we want, and use the light from that artificial star to inform us about how to change the deformable mirror. For me, this was an amazing night. We actually got telescope time on both telescopes. So you only need one laser per telescope, but it's like 2 laser pointers showing you the roadmap to the center of the galaxy. If you want to look up at the center of the galaxy, it's up this time of year. You find the constellation of Sagittarius, which is the teapot, and it pours into the center of the galaxy. Okay, so we now have this much more advanced way of correcting for the Earth's atmosphere, and we can see the stars at the center. Now we're going to look at a little animation here that shows a much smaller box than we were looking at before. Remember the on-off picture, blur, not blur? And there was a little inset. This is about the 1/4 of the size of the little inset. This is a ridiculously small field of view for most astronomers. But nonetheless, it shows the stars that we want to see. And it shows how they've moved over the last 24 years. So we've been very, very patient. I'm going to play this again, actually, because I just love watching it, to give you a sense. Now, there's all sorts of information color-coded in here, or coded in here. When you see the star with images, it's trailed by a solid line. So from the very beginning, we could take pictures, but the pictures got better, which meant we could see stars that we couldn't see in the beginning. So you'll see stars pop up that you didn't see before. Okay, so that's the progression in imaging. But images only show me how something's moving on the plane of the sky, 2 dimensions. And these are moving in space in 3 dimensions. And we pick up the 3rd dimension by taking spectra, which allow us to measure the motion along the line of sight. And that was only possible when adaptive optics came online. And I'm realizing I think I misspoke. So when things have an image behind, are picked up by an image, it's trailed by a dotted line. Let's watch this one more time. Yeah. And when it's got the 3rd dimension, it's turned into a solid line. And the whole thing ends highlighting my favorite star in the universe. Its name is SO2. Why is it my favorite star in the universe? It's because it taught us that there was a supermassive black hole at the center of our galaxy. It did that because we can measure that it took 16 years for it to go around. And we can measure the size of the orbit. And in particular, we can measure the size compared to its motion, its path, how close it gets to the mass that drives the motion. Okay, so what does that tell us? Oh, I can do this now. This tells us that while we knew there was 4 million times the mass of the sun located at the center of the galaxy inside a very large circle, we didn't know at the outset of this experiment that that was a black hole. What this experiment has done has been to show us that, in fact, if you look at a volume that's 10 million times smaller, you still see 4 million times the mass of the sun. Another way of saying that is that you've moved the case forward by a factor of 10 million for the existence of a supermassive black hole. And that's true not only at the center of our galaxy, but anywhere in our universe. So that's why this is so exciting. And to give you a sense of scale, we've confined it to a region that corresponds to roughly the size of our solar system. So again, think about it. We have 4 million times the mass of the sun inside a region that we experience as having just one sun's worth of mass there. So that's incredible concentration of mass, and therefore a case for a supermassive black hole. So we now have this wonderful case, and we say, fantastic. So you might ask, do you keep going with this? And I'm going to tell you, well, of course you keep going with this. This just gets better and better in a way that we couldn't have even predicted, given that we could barely convince the folks in the beginning to let us do a 3-year project, never mind a 24-year project. And the reason why this has gotten so interesting is that now you have a laboratory for understanding supermassive black holes. It's the closest supermassive black hole you'll ever have to study. And you can study it in a way that you cannot study anywhere else in our universe. It's the only galaxy for which you can measure the orbits of stars. So you have now effectively, through this, opened up a new approach to studying the physics and astrophysics of supermassive black holes. It's also, I think, a great demonstration here of how science is both driven by questions you know to ask, and sometimes by technology that shows you views of things that leads to questions you didn't even think to ask. Okay, so let's start from the point of view of the astrophysics. The astrophysics, as time has gone on, the astrophysics story has evolved a lot. When we first announced the result of the supermassive black hole, people used to ask, well, which came first, the black hole or the galaxy? It's kind of like the chicken or the egg. And of course, we had all sorts of answers for why one would happen versus the other. But today, we realize that's not even the right question to ask, because if you look in other galaxies today, we're able to show that the mass of black holes that are in those galaxies seem to correlate very well with the mass of the central part of the galaxy. And the scale of that is so different that that leads us to the conclusion that whatever process formed the black hole had to form the galaxy, and that there's some feedback loop that keeps the growth of these two very different scale entities in lockstep. Okay, so this is this correlation. So this is the thinking over the last roughly 10 years. So at the center of the galaxy, we have this unique opportunity to look at what kind of processes might be ongoing that keep the galaxy, well, let me put it this way, that enable us to understand the role that black holes play in shaping their host galaxies. Okay, so there were a couple of ideas that were out there about what we should find near this, a black hole at the center of the galaxy based on the notion that there was this connection. And one was that for old stars have been around for a long time. They've had a lot of time to interact, and they know where the life of the party is, so they like to congregate there. So the life of the party is the black hole. So things tend to sink, or what we call by dynamical friction, towards the most massive thing in the system. So you expect a very large concentration of old stars at the center of galaxies. And in fact, we even use that theoretical notion to find black holes in other galaxies because we look for the concentration of old star light to tell us that maybe there's a black hole. Okay, so that was prediction number one for the old stars. Then there's a prediction for the young stars. For the young stars, oh, and I should qualify what I mean by old and young. So old in astronomy means 1 billion years, and young means 1 million years. And the analogy with human timescales is, you can make the following analogy. If you compare the age of old stars to a human lifetime, then the age of these baby stars are the human gestation timescale. Okay, so these you really can think of them as baby stars, and you're looking at stellar nurseries, and you're trying to figure out how they form. And the analogy works really well because you need these things that begin as very fragile objects. They begin as big balls of gas and dust that are fragile, and you need these objects to collapse under their own self-gravity to form stars. Okay, now the problem with black hole is black holes are not nice to that process. You do not want your stellar nursery near a black hole, and that's because black holes have what's known as tidal forces. So if you've seen the movie Interstellar with those giant tidal waves that get created on the planet close to the black hole, that's what happens to young stars, is they get pulled apart. And that's because the tidal force means that if you fall in feet first, there's a larger amount of gravity on your feet than your head. So you get torn apart. And astrophysicists like to call this process, or popularize it, to call it spaghettification, like a spaghetti. Okay, these are two young stars I'm particularly fond of. They're my little young stars. They're a little older these days, but I would not want them near a black hole. Okay. Now, what do we see? So we've got two predictions. Lots of old stars, no young stars. So let's look at what the observations show. And what I love is it's the exact opposite. Okay, so the color coding here, and this is now a 3-dimensional picture, is the old stars are orange, the young stars are blue, aqua blue, and then the pink stars we didn't even think to make predictions for. So that's 3 new mysteries. So again, wow, questions we didn't even think to consider, and that means that drives both theoretical work. So the theorists go to work in terms of coming up with new ideas. How do you get the young stars there? How do you get the old stars there? And what in the world are those pink stars? Which I'll get to in a minute. Okay, so lots of work from a theoretical perspective, and as an observer or somebody who uses a telescope, my perspective on this is, what other observations can I make that gives us new insight into what's going on? One of the key things that we can do is just keep going. Time really helps. The longer you go, the further you are from the black hole, the longer it takes for stars to go around. So if I measure for a longer and longer amount of time, I can actually learn about the orbits that are more distant from the black hole. So I start with a really kind of myopic view of what's going on at the center of the galaxy, and over time I get a more expansive view. And it's been fascinating what's dropped out of this, and again, totally unexpected. So you can see, hopefully in this animation, that as we pull back from the center and look at the kinds of orbits that we're measuring, you see a set of young stars that form a disk. It actually looks completely like a scaled up version of the solar system. And it works perfectly well. The ratio of masses between planets and the central host star in our solar system is almost the same as these massive stars compared to the black hole. So that's exciting, and we're going to use insight from how solar systems form to understand what's going on here. So we think that what happened is that when these stars were being formed, there was a disk of gas and dust that created both the stars that then orbit in that plane, but also probably provided a lot more gas at the center of the galaxy. And that suggests that our galaxy was probably much more active in the past. It was probably much more akin to those active galactic nuclei, those prima donna galaxies that we showed in the beginning. Our galaxy was actually probably more like that than it is today. Today, we are completely ordinary, garden variety, nothing special about us state. And that's because that gas has now been locked up in the stars. Okay, so that's idea number one for the young stars. So I kind of like that idea. We're still working on it, but that's starting to, I think it's really gelling in terms of both the theory and the observations. Old stars, don't know. I'll just say, don't have a clean answer. Lots of ideas, don't know. But what I'm second most excited about are the magenta stars. We think those are probably pairs of stars that the black hole drove to merge. So in other words, it's an interaction that people didn't think about. And when they merge, they become really fat. And when they're really fat, really big, just really enormous, then the tidal forces are bigger, so they get pulled apart. And that's what we see. The magenta stars are the stars that we see the process of being disrupted. The surfaces are being pulled apart. So really exciting, and probably connected in a way that I could not have anticipated to the LIGO results. Okay, that's fun. Okay, now what am I really excited about this year? We are excited because SO2 is going through its closest approach right now. And I cannot believe I'm here right now. But this event, SO2 goes around every 16 years. And there's an event that basically lasts 6 months. So admittedly, it's hard to be here. It's a very special time, but it's all this season. And what are we trying to do? We're trying to understand the curvature of space-time, how space and time get commingled or mixed when you get close to the black hole. So there's that classic picture of what happens near a black hole, the funnel you see in science museums, and that's what you're seeing here. It's 2 dimensions of space and 1 dimension of time. And we want to see how both light is affected by having to make its way out of that well, what we call the potential well, and how the star's orbit is affected. Okay, I'm going to skip that because that's really crappy. Actually, no, I'm not. I'm going to go back. A little tacky, but we're going to do it. You can see here, actually, what you're also seeing is how new this is. The graphics are different, and that's because we're in the middle of this. So we don't have the clean. So you're getting the first look. I'm not going to show you the answer. I can't. I'm strictly sworn to secrecy. But I want to show you, this is a blown up version of what SO2 might do. It's going through this curvature of space-time. That closest approach, the forms are most extreme. To test, you need to know the shape of the orbit. So you basically need the history of having already seen it go once around. And the next time it goes through closest approach is your opportunity to do this unique test. So you can think of it as the Wild West. There are 4 theories of 4 fundamental forces. Gravity is one. It's the least tested. And nobody has ever tested it this near a supermassive black hole. So you're exploring an unknown frontier. Have no idea what's going to happen. This is a little bit more detail. Red is the line of sight measurements. Green is the images. And you have to measure when it's at a maximum and a minimum. And I'm just going to say the shaded part is our galactic center season. You can see it from 6 months roughly because the Earth goes around the sun. And so I'm just breathing a sigh of relief of thanks goodness all 3 events happened in that window. And we'll probably be sharing our results when we finish with this window. So it's an exciting, exciting time for us. All right.